mx double prime equals negative kx, we assert that x equals sine of omega t solves this for an appropriate value of omega. Now, I'm just kind of giving the solution away, but you have to then substitute sine omega t for x in here and see what you end up with for omega. It turns out that the equation will be solvable for omega. It's quite easy to do that. So, the second derivative of the sine of omega t, and you have to use the chain rule, so you have to be a little bit careful, but that's about all. The derivative of sine omega t is what? Omega times the cosine of omega t. And the derivative of cosine omega t is negative omega sine omega t. So you got an omega with both derivatives. So you're going to get a negative omega squared sine of omega t. And you don't have to understand the words that I just said. Don't try to remember the words that I just said. Just take the second derivative of this. Then, if you don't get this, go back and listen carefully to my words. Okay. On the right side, we have negative kx, so that's going to be negative k times sine omega t. So we have this equation. We divide both sides by sine of omega t, and we get negative m omega squared equals negative k, so that omega is the square root of k over m. Now we could say plus or minus the square root of k over m, and actually that wouldn't hurt because omega could be positive or negative. We could, that's not really going to make a difference, because we'll just about always make omega positive. But there are cases where you'd want to make it negative, so this allows you to do that if you need to. Also, if omega equals square root of k over m, b sine of omega t is a solution. So you just multiply the sine by something. You're multiplying the sine by b. Well, how would that change it? We'd have a b here, we'd have a b here. Well, the b is not affected by the derivative, so we could take the b out of here. We have a b over here, so divide both sides by b, and you still have this equation. So b just divides out of the equation if you have one. Now, if we'd use cosine of omega t instead of sine of omega t, you can verify that it would have worked. We'd have had negative omega squared cosine omega t here. We'd have had cosine omega t here. We'd have still divided out the trig function, and we'd have still gotten this and this. If you have a multiple of the cosine of omega t, it's still going to work out. So you should then substitute b sine omega t plus c cosine omega t in here and verify that, again, you get the solution omega plus or minus the square root of k over m, so that this is a solution for that value of omega. Also, sine of omega t plus phi, that a sine omega t plus phi, is a solution. Okay, just plug it in. You know, it's just like when we had b sine omega t. The phi isn't going to affect anything with the chain rule because the derivative, phi being a constant, implicitly, the derivative of omega t plus phi is still omega. So we're still going to get an omega for the first derivative, another omega for the second derivative, and we'll still have, and also taking the derivative doesn't affect what's inside here, doesn't affect your innermost function. So we're going to have a sine of omega t plus phi here, and a sine of omega t plus phi here. We divide them out, we still get the same thing. Okay, so in general, your solution to this differential equation will have either this form or this form. And these forms are connected not only by the fact that they are solutions to this differential equation and equivalent solutions, they're connected in a very simple way. Oh boy. By trigonometric identities. The identity for sine of alpha plus beta or the cosine of alpha plus beta allow you to connect this with this. This is like a sine of alpha plus beta. Just apply that identity, you're going to get a sine times a cosine and a cosine times a sine, or a sine times, yeah, you're going to get something of that nature by the trig identities, and you'll be able to tell how the coefficients b and c. B is going to be like the sine or cosine of phi, c is going to be like the cosine or sine of phi, depending on just what that identity is, and I'll let you worry about that. I don't even remember what those identities are because I can derive them in seconds from the Euler formula. E to the I pi equals cosine, e to the I theta equals cosine theta plus I sine theta. They're a little tougher to do using triangle geometry, but they can also be done that way. Okay, well, this is quite relevant to what we did in lab, so we'll talk about that connection briefly.